Okay, Assalamualaikum and very good day to everyone. So today we will continue our second lecture regarding on chapter 2, which is part 2, that we will cover around for the temperature effect on the IV characteristics, Zener diode, and also the additional information that will not be covered in your test regarding on the temperature coefficient, power dissipation, and power derating. Right? So this is the learning outcome that students will be able to achieve at the end of the lecture. All right. So now let's look what is the IV characteristics of the diode. Okay, so we have learned before that when the diode is in a forward bias configuration, and how to determine the forward bias configuration. Okay, if we can recall again, when there is a diode, which is this part is known as a anode and this part is known as a cathode, right? Anode and cathode is connected to the positive side of a terminal, and the cathode is connected to the negative side of a terminal. So this configuration we said is a forward bias configuration, where it allows the current, okay, it allows the current to pass through the diode. Okay, so how is this happen, or how is this how the current can pass through the diode? So if we can recall back what we have learned, this is because of the existence of the free electrons. Okay, more free electrons, okay, is applied. Okay, where this is the P region, region, and this is the N region, and we can see this is the layer, okay, the positive layer and the negative charge layer, okay, that form the depletion layer. Okay, so when the configurations of the diode is connected to the DC source is on a forward bias. Okay, so we can see that there will be more free electrons exist in this area. Okay, that free electron exists, yeah, from that supply from the DC source here. Okay, will be inject to this diode. Okay, and that's make the movements of the free electrons becomes more. Okay, there are going to be more free electrons inside the N region, and this will make these electrons, okay, can passing through the this depletion region, okay, and make this depletion region can broke or can fall down the depletion region. Okay, and therefore the free electrons then will be able to flow along this along this diode. And what will happen in this case, when the diodes is in forward bias configuration, the depletion region will become thinner and thinner. Okay, so this allow the current through a diode can be measured. Okay, however, if the diode is in a reverse bias configuration, okay, current except for a negligible reverse current exists. So what is this negligible reverse current? So if we can remember what we have learned in our previous slide, okay, this is the IS, okay, which is the saturated current that happens when, okay, if we can draw the diodes configurations here. Oops, sorry, this is supposed to be negative terminal, and this is the positive terminal, and this is the N region, and this is the P region, and this is the positive layer, and this is the negative layer. So when the connection, the P is connected to the negative of the terminal, and the N region is connected to the positive of the terminal, so we know this is the positive and the negative, the anode and the cathode. Okay, so the electrons that supply or come from the terminal, okay, from the DC terminal, okay, will then be assembled at this layer. Okay, will then be assembled at the negative layer. Okay, instead it goes to combine with the whole. Okay, and so same goes to the positive. Yeah, so due to this, it will mix all the positive layer, okay, that has inside the N region, okay, will then become assembled and in order to attract with this negative charge here. Okay, so it makes the depletion region at some point will become at a maximum thickness. Okay, so the positive and the negative charge then will form the electric potential. Then that potential will create voltage, and when there is a voltage, of course there is a current. Okay, there is a current, yeah, that is formed here. All right, so this current is known as IS. Okay, IS, or some book also use denote this current as IR. Okay, it depends on what books that you refer. So this IS usually is very, very small and it can be negligible. Okay, so the reverse bias prevent currents as long as the reverse bias voltage does not equal or exceed the breakdown voltage of a junction. Okay, so however, let's say if you apply more voltage here, okay, if you increase the value of the voltage, what will happen to this diode? It will fall into a breakdown voltage. And what will happen in this breakdown voltage? Okay, we can see this later. Alright, so now let's look at the forward bias measurement. So we can see here, so V bias here is the external DC source. And VF is the voltage across a diode. Okay, let's say the configurations of the diode. This is the P and this is the N. Alright, and the IV is the current that flow inside the circuit. Okay, so same goes to this here. So VF, we has IF here, and we have V bias here. Okay, let's say the amount of V bias that we apply to the circuit now is not so high. Okay, when we measure, there is a diode here. Okay, when we measure a current across the voltage across the diode here, we can see the voltage now is not so high. Okay, it is not so high. This voltage will not be exact as this voltage. Why? Because there is a resistor here. So what is the function of this resistor? The function of this resistor is to limit current. Okay, is to limit current so that there's gonna be no excess current suddenly flow inside this diode. So it's control the amount of current that flow inside that particular circuit. Okay, so that's why the voltage of the across the diode is not as the same voltage that we apply at the DC terminal. All right, so we can see here the voltage here is less than 0.7. By right, what is 0.7? What we have learned from our previous lecture is the voltage barrier potential value. Barrier voltage, variable voltage that is required in order to make sure that the electrons, okay, this is P and this is N, that free electrons able to move, yeah, okay, and this is positive, okay, that free electrons remaining at the N junction able to move and diffuse to the P region. Okay, so that is the value, minimum value of voltage, okay, that should allow the free electrons that exist at the N layer, N region to diffuse to the P region. Okay, so we can see since that it is not enough yet, it is lesser than 0.7, so the value of current that flow that flow inside the circuit is not so high. Okay, we can see that. However, when we increase the DC voltage, okay, much higher now, okay, in this case, okay, so we can see here the voltage across the diode now is nearly constant and remains. It remains and nearly constant approximately 0.7. So in this case now, all the free electrons, okay, at the end region are able to move, okay, with the extra electron flow, okay, that is supplied from the DC terminal now. Okay, all the free electrons now are able to move to diffuse to the P region. Okay, so we have more numbers of free electrons that exist inside the N region. Because of what? Because of the coming from the DC voltage that we applied to this particular circuit. And due to that, we can see here, once it is remain constant and approximately 0.7, what will happen to the depletion layer here? It will start to break. Okay, it will start to fall and it will become thinner and thinner. Okay, the size will become thinner, and this will allow the currents now to pass through lots compared to when the voltage across the diode is not reach 0.7 volts yet. Okay, so if we can draw the IV characteristic, which is the value of the current against the value of the voltage across the diode, VF, value of the voltage across the diode against current. Okay, we can see before 0.7, will there be any current? Yes, there is current, but the current is a very small current. So we can see between, before 0.7, the current inside that circuit is very small. Okay, and it increase gradually, it increase slowly. So VF here is voltage across diode, and IF here is current flow and the circuit. Okay, all right. However, when the V bias, okay, which is the external voltage, is more than 0.7, we can see there is a transition where the graph now becomes increasing aggressively or extensively. Okay, it starts to increase rapidly. All right. So at the transition here, okay, at this part, the transition part here is known as knee. Okay, the transition from the graph gradually increase to rapidly increase is known as knee. So that's why in some case, okay, or in sometimes we also mention the 0.7 volts as the knee voltage, which is VK. All right. Or in there is also another name of this 0.7, which is also known as voltage drop. Okay, VD. All right. So don't get confused when you see a different terms in some different reference book, because all of this is same. Knee voltage, voltage drop, or what we have learned before is barrier potential or barrier voltage, right? Is VB, if I'm not mistaken. All right. So all of that is same. All right. So now, if we can expand, at the knee there, okay. If we can expand, we can see the dynamic resistance RD decrease as you move the curve, indicate the decrease of the value VF over ID. So we can see at this part, at this part, since that the graph is moved rapidly, so we can say that the internal resistance, okay, inside the diode is decreasing, okay, because we know V is equals to IR. Okay, when your when your I increase, okay, then your R will decrease, right? In order to make your V increase. Okay. Now, how about the characteristics here? Okay, what we can see here, as the V bias continue to increase, remember, V bias is the external DC source. Okay, the IF continue to increase, okay, very rapidly, but VF increases only gradually above 0.7, okay. The small increase in VF above the barrier potential, okay, so this is the barrier potential due to the voltage drop across the internal dynamic resistance. So why is it is increase not as rapid as once at this area? Because of there is an existence of dynamic resistance. So this dynamic resistance is also known as internal resistance that is happen inside the diode, okay, because of the barrier because of the depletion layer, okay, because of the existence of the depletion layer, it makes the current not able to flow as high as once the value of the V bias above 0.7, okay. So normal operation for a forward bias diode is above the knee of the curve. So usually, in order to make sure that the diode is in a working mode, okay, in an operating mode, usually we have to make sure that it must be on the above the knee, meaning that at this point, okay, any point at this point, meaning that the diode is in the normal operation. But in this point, okay, at the lower point, this part, the diode is not fully operate yet, meaning that it is not achieve its maximum limit yet, okay, it is not function to the maximum yet. All right, so we can see here the relation between the barrier potential and the temperature. Okay, how if, let's say, we increase the value of the temperature surrounded of the bias? Okay, so when a diode conducting, okay, we have a TJ. So what is TJ? TJ is the temperature inside a diode, okay, right at the PN junction. Where is the PN junction? At here, okay, right at the PN junction here. Okay, and TA is the ambient of the temperature, meaning that the surrounding environment of the diode, which is at this part. Okay, so this is TA, this is TJ. Okay, so we can see when your TJ is larger than TA, okay, what will happen by right? All the free electrons, okay, there is a depletion layer. Okay, in a normal situation, of course, there's gonna be a depletion layer here, okay, where there is a strong connection, strong electric field that is formed between the positive and the negative charge. So what happened to these free electrons here? That is not allowed to diffuse to the P region. It are not able to move. Okay, it doesn't have enough energy to pass through this barrier. Depletion layer. Okay, so now let's say if we increase the temperature now inside this, okay, inside this diode, we increase the temperature. What will happen to all of this free electrons? It will become aggressively. Okay, just like human, right? When we are hot, we cannot stay still. All right, we will become aggressive. So same with the free electrons here, it will become aggressively. So when it becomes aggressive, what will gonna happen? It will move aggressively. So when it move aggressively, it will start to diffuse into the depletion layer and makes, okay, the energy, okay, the energy field that form inside the depletion layer to become loose. Okay, it will collide with this bonding between the positive charge and the negative charge at the depletion layer and make their energy to become loosen their energy. All right, so it will then create a valence electron at this depletion layer and makes the depletion layer become narrower. Okay, so it will makes the barrier potential here become lesser and lesser. So we can see here what will happen when we increase the temperature inside here. So it will make, instead of 0.7 volts, your value of barrier potential at the beginning, to reduce the value to become perhaps 0.6, 0.5 volts. Okay, it will reduce the value of the barrier potential inside here, okay, because of the increase of the temperature. Okay, all right. So the barrier potential decreases as the temperature increase. Okay, so let's say you don't want to do anything with the external DC here. We don't want to apply any external DC, and then we don't want to do anything. So we just want to add some temperature to this diode. So due to this, increasing of the temperature, it will make the barrier potential here become lesser. And it makes the depletion layer becomes narrower, and therefore the value of the barrier potential will become lesser. So instead of 0.7, it will become 0.6 or 0.5 or 0.4. Okay. Alright, so now let's look the IV characteristic for reverse bias. Okay, so usually IR or IS, yeah, is so small that and it can be neglected. So you can see here the range of the current that can be produced at the reverse bias is very small, around microampere, compared to the reverse bias. If you realize, the value is around milliampere. Okay, so 2 times larger compared to the reverse bias condition. So that's why it is almost can be neglected. So at this high energy electrons go through the depletion layer, and they have enough energy to go through the N region as conduction electrons rather than combining with the holes. So we can see we did know that all the electrons, yeah, they are going to combine the negative charge and the positive charge together, okay, instead to go to the to combine with the conduction electrons that is at the N region. Okay, so at this situation, okay, however, when you increase the voltage, okay, the external voltage here, okay, oh sorry, this is wrong, this is supposed to be, when you increase the voltage, let's say you increase the external voltage, okay, you increase the external voltage, what will happen? Okay, there is a breakdown. Okay, what we have learned just now is there is a breakdown. So breakdown means when this voltage, the voltage that we apply during the reverse bias is applied is too high, okay, and there is an avalanche. So what is avalanche there? The multiplications of conduction electrons at the N region, okay, all right, at the N region is known as the avalanche situation, and this is called as the breakdown voltage. And you can see at this part, so this is the avalanche region. So at this avalanche region, usually it will make the diode becomes damaged, and it will break the diode, yeah. Okay, so avalanche happen is because of due to the increase of IS that we have learned before, okay, IS, which is the saturation current, yeah, IS, and therefore sufficient to release additional carriers through collision. Okay, so it will mix. So that's why you can see here that there's a sudden drop of the current, and however, the value of the current is very small, which is microampere range. Okay, and due to this, it will mix the diodes become damaged and burning. Okay. Alright, so let's look at the breakdown voltage here. Okay, so this value of breakdown voltage can be altered according to how did you dope that particular diode. Okay, so let's say when you make the doping is higher level, okay, so we can see here the value of the voltage for the diode to break down is much smaller compared for a low dop diode, okay, which is the value of the voltage that will damage the diode is slightly higher compared to the high dop voltage, okay. Right, so IR, usually IR or IS can cause an overheating and makes it is possibly damaged lah. All right. So this is the summary of the IV characteristics. Okay, we have learned about the forward bias, where at the forward bias condition, it's able to conduct currents, and at the reverse bias condition, it is blocked the current. However, if the voltage is increased, it will go and it exceed the breakdown voltage. So it will make the diode to overheat and damage. So all of this only true if it is happening to the regular diode that has been manufactured to work only in a forward region. Okay, so however, there is another diode, special diode that is specially designed to work only in a breakdown region. So this diode is known as a Zener diode. Okay, it's known as a Zener diode. So now let's compare the operating between the normal diode and the Zener diode. Okay, so in a normal diode, we know it only allows to work in the forward bias region, and before the breakdown voltage, it's still working, but it doesn't know, it makes no current flow inside that particular diode. Okay, all right. However, so this is a normal diode. So normal diode, usually it works as a rectifier. So it is very important for you to remember, yeah. Normal diode is work as a rectifier. Okay. However, for a Zener diode, okay, Zener diode, it only works well, okay, at this reverse breakdown region. Okay, meaning that the value of the voltage must be larger than the breakdown voltage, okay, at this shaded area. All right. So let's learn more about the Zener diode. Okay, so we can see here, Zener diode is designed for the reverse breakdown region. So that's why it is can work in the reverse breakdown region. Yeah. So because of the configuration must be in a reverse bias configurations. Yeah. So it operates same as a regular diode in forward bias connection. So at this forward bias connection, okay, at this forward bias, at this area, the Zener diode work or not? Yes, it still work. Okay, it still work, but it works as a rectifier, same as the normal diode. Okay, it works same as a normal diode as a rectifier. Okay, in this region it not work. It doesn't allow current to pass through the diode. However, once the value of the voltage is over the breakdown voltage, it then work as a Zener diode. Okay. So direction of conduction is opposite, but polarity of VD and VZ are the same. So we can see the polarity now. Okay, so in the normal diode, the voltage is named as VD. Okay, and the Zener diode, the voltage is named as VZ. Okay, the current will still flow from the positive to negative of the terminal. Okay, of the V bias, yeah, of the DC source terminal. Okay, however, the current that is flow inside the diode is represented as ID, but current that flow on the Zener diode is represented as IZ to differentiate it. Okay, so we can see for Zener diode, there's like a curl here. Let's look like a Z letter. Okay, to differentiate between the normal diode and the Zener diode. All right. So this will gonna be the negative side, and this will gonna be the positive side of the diode. So that's why it will become in reverse bias condition. All right. So what is the function of Zener diode? So Zener diode is, the function is to maintain a specific voltage across the terminal within the given limits of line or load change. So in other words, we said Zener diode is used as a voltage regulator. Alright, so this is the original or the real device of a Zener diode. Okay, so it looks like a metallic color. So usually Zener diode is made from the silicons. Yeah. So this is the voltage regulator. So what it means by voltage regulator? Okay, let's say we have some voltage supply here. Okay, so when there's an arrow here, it means that this voltage supply is can be changed. Okay, the value can be changed, all right, into some value according to that particular device, from what to what value of voltage that it can supply. All right, so but however, since that there is a Zener diode connected here, okay, so when the Zener diode is connected in this circuit, we can ensure, okay, we can make sure that the output of the voltage is depending on the specifications of the Zener diode voltage. Let's say this Zener diode can operate at 10 volts. So meaning that the output of the voltage for this particular circuit will remain 10 volt no matter how did you change or how did you regulate this DC source. Okay, all right, so it will mix throughout the circuit. The voltage at the output maintain 10 volt across the load. All right, so that is what we call it as voltage regulator, or that is the meaning of the voltage regulator. Okay, so usually it is used to maintain the voltage supply. All right. So now let's look at the reverse bias, reverse breakdown. So breakdown voltage is set by doping level, as I mentioned just now. So there are two breakdown mechanisms in Zener diode. We have a Zener breakdown and avalanche breakdown. So same with normal operating diode, Zener diode also have the avalanche, where at this avalanche it will mix the Zener to damage. Okay, same as a big diode that we have learned before, that at the avalanche region it will make the diode overheating and damage, right? So same goes Zener diode also, although it works in the breakdown region, it has a limit. Okay, over that particular limit, it fall on the avalanche breakdown, where it will make the diode, Zener diode, overheat and damage. Okay, so usually the breakdown of the Zener diode, it must be lesser than 5 volts. Okay, so if it is more than 5 volts, it will fall into the avalanche breakdown. Okay. So Zener breakdowns occurs in a Zener diode at low reverse voltage. So the breakdown voltage is set by carefully controlling the doping level. Okay, so a Zener diode is heavily doped to reduce the breakdown voltage. So still remember, yeah, the one that we have discussed earlier. When the doping level is high, this voltage will become lower, okay, compared to the low dope. Yeah, so okay, back to the slide. Okay, so this will make the Zener diode has a very thin depletion region. Okay, so the reverse breakdown voltage remain almost constant even though the current changes drastically. Okay, so we can see here at the graph here, where is the graph? Okay, yeah, you can see here this is almost a straight line. Okay, so although the voltage, the voltage is changing, okay, it will make although the voltage is not changed, okay, in one value only, okay, it will make the current flow inside that particular circuit is to move rapidly, okay, to change that drastically. All right, because of the straight line. Okay, so this is what the sentence here means. So now let's look avalanche breakdown. So avalanche breakdown occurs in both regular and Zener diode. So this is happen when the high reverse voltage is applied to that particular diodes lah. All right, And a Zener diode is much like a normal diode. Okay, it has the avalanche region, reverse breakdown region as well. However, we know it works in a reverse bias connection and in the reverse breakdown region. Okay, so this is the typical of Zener diodes. A typical normal operating for a Zener diode. Okay, so it's usually on this particular stage. All right. Okay, so for a Zener diode, okay, let's look at this. Okay, for the we know at this particular region, yeah, at the VZ here. Okay, at the VZ here. So this is the VZ, all right. So VZ is the value of the breakdown voltage that makes the Zener diode starts to turn on or starts to work or start to operate. Okay, and then if you can look at the graph here, okay, if you can look at the graph operating here, before this VZ, okay, the graph of the IV characteristic is like a slow change at this particular part. Okay, and suddenly when it reach the VZ voltage, it start to decrease drastically. Okay, it start to decrease drastically. So at this particular part, same as what we have learned in the normal operating diode, when there is a transition between the slow increase and drastically increase, we call it as knee. Okay, we call it as knee. So that's why if you can see here, there is an IZK. So IZK here refer to the Zener knee current. Okay, Zener knee current, which is a minimum value of the current, okay, in order to make or to keep the Zener diode in a breakdown, meaning that a starting voltage for a Zener diode to start to operate. Okay, all right. And IZ, okay, IZ is a Zener test current. Okay, in some book it's or in some reference book you can see it it represented as IZT. Okay, and in some book it refers as IZ. Okay, so this is actually a Zener test current, meaning that this is the value of current that a nominal VZT is specified on a data sheet. Okay, so this is the value of optimum current that the Zener can works on. Okay, when I say it optimum, it means that the best value of VZT that will produce the best current for the Zener, okay, to works on. Okay, so usually this value or this IV characteristic you can find in a data sheets lah. So because different Zener diode has different value of test current. Okay, and how about IZM? So IZM is the Zener maximum current. Okay, meaning that, okay, these above this, okay, at this point, this is the maximum current that the Zener can produce. Over this, it will make the Zener diode damage due to the excessive of power. Okay, due to the excessive of power. All right, so we can say here, low voltage Zener less than 5 volts operate in the Zener breakdown range, and those designed to operate more than 5 volts operate mostly in avalanche breakdown range, and Zener are available with voltage breakdowns at 1.8 to 2.0 voltage. Okay. All right. So we can see here. This is the Zener. So for the ideal characteristics of Zener, okay, before the VZ, okay, before VZ, the value of the reverse current will be exactly as 0. Okay, compared to the practical mode of Zener, before the VZ, you can see that there is a slightly increase of currents here. Okay, so sorry, slightly decrease, not increase. Yeah, slightly decrease of current here, but it is very, very small lah. But if it is an ideal characteristics of Zener, it will be exactly as 0. Same goes to the forward bias. Yeah, it will be exactly at 0. Okay, it will not goes like this. Okay. And you can see here another ideal characteristics of a Zener diode. Okay, when it is an ideal diode, you can see it is exactly as straight line compared to the practical diode. There is like a slope here. All right, so the constant voltage drop is represented by a DC voltage source. Normally, external R is larger than ZZ, therefore ideal model is usually used. Okay, so at the ideal model, we assume that there is no internal resistor happen inside the diode. Okay, so same goes with the normal diode. Okay, I think I didn't have discuss for the normal diode yet for the ideal characteristic. So same goes for the normal diode. At the ideal characteristic, okay, the diodes is like this. It works like this. Okay, it is not like what we have discussed so far. It is like this, right, where it has the knee. Okay, there is a knee. So for the ideal, there is no knee here. Okay, for ideal, there's no knee, meaning that there's no transition. Okay, because of there's no dynamic resistance, no dynamic resistance or internal resistance inside that particular diode. Compared to the practical diode, it has the dynamic resistance or internal resistance. Okay, but it in our practical use, it's very hard. We can't obtain this ideal diode. All right. So let's look at the characteristic curve here. So we can see here at the forward bias, okay, the Zener will work as a normal diode, and we said on the forward bias connection, the Zener diode will act as an rectifier diode. Okay, so it only allow currents when it is a forward bias. Okay, it works as normal diode. Okay, equals to normal diode. All right, and before the breakdown region, okay, before the breakdown of VZ, the diode will gonna be off diode. Okay, however, when the configuration is reverse bias, the Zener diode starts to on. Okay, all right, and it starts to work as a regulator, voltage regulator. All right. Okay, so this is an additional information for you guys about the temperature coefficient. So temperature coefficient is the percent change in the Zener voltage for each degree centigrade change in the temperature. Okay, so a positive temperature coefficient, meaning that you have the VZ increase, which is the Zener voltage, increase with an increase in temperature. Okay, talking about temperature, I think I forgot about the to mention that the temperature increase here. How much the temperature increase? Okay, let's discuss on the forward bias in terms of temperature. Okay, in terms of temperature, let's say you are now increase the temperature. Okay, so this is the graph that shown here is on 25 degrees. Okay, let's say this is on 25 degrees. All right, how if you are changing now the temperature to increase temperature? You increase the temperature instead of 25 to become 125. Let's use different color. 100. Oh yeah, let's use different color. Yeah, now it is 125. Okay, when you increase to 125, this graph here, the graph here will start to change. Of course, it will change. So it will change in terms of what? It will change to the left. Okay, all right. So now let's draw the changes. Okay, So it will change to the left when the temperature increase. Okay, when temperature increase, it will change to the left, and therefore it will change as well the value of the what we have discussed just now. Okay, the value of the barrier potential also will be changed, right? So it will mix the value of the potential change to here. Okay, becomes reduced, yeah, somewhere around here. Okay, let's say 0.6 or 0.5, like that. All right, so how about if you decrease the temperature? So when you decrease the temperature, the graph now will start to change to this side. Okay, to this side. Okay, let's say this is negative 75 degrees. Okay, so when you decrease the temperature, this is when you increase the temperature, yeah. So this is when you decrease the temperature. Okay, so temperature usually will change. Okay, temperature usually will change. Okay, the temperature change usually around in forward bias. This is only happens on the forward bias. Okay, for the silicon diode. Okay, for a silicon diode, the temperature, yeah, the graph will change. The IV characteristic, okay, will shift to left at rate. So this is the rate of the shift, yeah, 2.5 millivolts centigrade degree increase in temperature. Okay, so when the temperature increase, it will move to the left at the rate of 2.5 millivolts. Okay, all right. Okay, so when the temperature is decreased, it will move to the right at the rate of negative 2.5 millivolts. All right, so this has happened at the forward bias. How about at the reverse bias? Okay, so at the reverse bias, let's say in this situation, this is on the normal room temperature, 25. Let's erase this. Okay, all right, 25. But let's say we want to increase the temperature. Okay, so when you increase the temperature, what will change is this line. Okay, before this line will go down, and this line will go to the left. Okay, so how it's gonna be? It will be like this. Okay, it will be like that. All right, so you can see the like a constant line here is shift to down. Okay, it will gonna shift to down, and the decreasing slope here, it will shift to the left. Okay, it will shift to the left, right? So this is when you increase 125 degrees. Okay, how about when you reduce the temperature? So when we reduce the temperature, just now I'm using what color? I didn't remember. Okay, green color. So when we reduce the temperature, okay, the line will then be like this. Okay, it will be like that. Okay, it will go to upward, which is near to 0. Okay, it will near to 0, and this line will go to the right hand side. So in reverse bias, usually the saturation current of silicon diode doubles for every 10 degrees rise in temperature. Okay, let's write this. Okay, in reverse bias, okay, reverse saturation current of silicon diode doubles for every 10-degree rise in temperature. Okay, all right, so it will increase here. So this is the saturation current. Okay, this is the saturation current. So 10-degree rise, it will doubles. It will doubles. Okay, it will doubles. Okay, right, you make it more lower lah, the value of the current. Okay, so for this part, okay, for the temperature coefficient here, this will not be covered in your task, so I leave this for your own reading. Okay, so therefore I stop here. Thank you very much and see you on the next lecture.